Hi everybody. Just a few moments ago, we finished a synchronous moment in class where we went through these week 3 problems, summarizing the material between 13.1 and 13.3. For those of you who weren't in class, I was going to record that session so that you could watch it later on. Unfortunately, due to some bandwidth limitations here at my house, I wasn't able to record that session. It was interfering with the video quality. So what I'm going to do instead is go through the problems again here, recording my solutions to them. And I'm sorry it's not the same as that interactive class period, but we'll try to do the same things kind of and have the same thoughts come up. And so this problem set that you'll find on Moodle starts with the vector function r of t equals sine of 2t plus sine of 2t, sine of 2ti plus sine of 2tj plus root 2 cosine of 2tk. And then the question to start has nothing to do with that. It's like, what's the big idea in the sections 13.1 through 13.3? And the students that were in the synchronous chat that we just had started throwing things out that came up, right? And so we have this idea of vector function, right? And that's a huge idea that runs throughout the section, right? And then we listed all the calculus things that we learned. That we took limits, we found derivatives, we found antiderivatives. We had definite integrals, indefinite integrals. We even found arc lengths, right? And all this calculus that we had done previously comes back up here and with these vector functions. And I said, that's great, absolutely. Those things all come up. But what's the big idea? What's the unifying thing? And then someone says, well, the unifying idea is actually that every time we went to do calculus on a vector function, we just did the calculus we already knew on the component functions. And so that really is the big idea. To do the calculus of vector functions, we just do calculus on the component functions. And those component functions are scalar functions, right? That's just doing calculus that we already know how to do. And that's the exciting thing, is that this unit's full of doing calculus, relationships between position, velocity, acceleration, arc length, and these are all calculations that we've actually met previously and now just apply to concepts in space, and right now, specifically, to vector functions. All right, so moving along, after we have that conversation kind of about the unifying idea through all of 13.1 and 13.3, and even the rest of chapter 13, we're left to deal with this position vector. And the actual calculus involved in analyzing this particular vector function is not that difficult, so hopefully we're going to build up to something that's actually interesting. But in question number 1, dealing with that vector function, we're asked to find the velocity and acceleration vectors. We're asked to take 2 derivatives. So the velocity vector is the first derivative. So just need to remember the chain rule. All right, and then the acceleration vector, one more derivative. Still remembering the chain rule. Okay, so there I have it. Position, velocity, acceleration, just a bunch of derivatives. Okay, so, and again the idea, right, to do the calculus of this vector function, we just take derivatives of the 3 component functions. Then we're asked to find 2 dot products, right? Find r dot v and v dot a. If you're watching the video rather than having seen this in the class session, go on and pause the video here. Take those 2 dot products and see what you get. Okay, So let's take r dot v. Multiply the I components together and I get 2 sine of 2t cosine of 2t. Multiply the j components together and I get the same thing. Well, I'm going to add, so I'm just going to call that 4 of those. And then when I multiply these together, I get minus, let's see, root 2 times 2 root 2 is minus 4. And then I get the sine t and the sine of 2t cosine of 2t again. So those cancel out and give me 0. The position dot the velocity, always 0. And that's going to allow us to conclude something important here in a moment. But now the velocity dot the acceleration. Well, if I look at it, I get minus 8 sine times cosine, minus 8 sine times cosine. So minus 16 in total, sine of 2t, cosine of 2t. And here, let's see, that's going to be a positive 8 times 2 is 16. The acceleration dot the velocity is also 0. Okay, so I have r dot v is 0, v dot a is 0. So I've found the dot products. And then the very next question, what do the dot products in the previous question tell us? So what does this mean? Well, right away, when two vectors have a dot product of 0, it means they're orthogonal. So r and v, the position and the acceleration, are orthogonal. They're perpendicular to one another. And v and a are too. Always, for every value of t, right? In general, right, I'm not always just going to get a number when I dot product two vectors together, right? I might get a function on t, right? The angle doesn't always have to remain fixed between two vectors. So it's like super special, I get a constant, and even more special that I get 0. Okay, does that let us conclude anything else? What else do we know about vectors whose dot products are 0? Or better said, what else do we know when position and velocity dot product together to give us 0? Well, r dot v is the same thing as r dot dr dt. And when a position function is derivative or equals 0, it actually implies to us that its magnitude is some constant. Well, v dot a is the derivative, v dot its own derivative. And so the same conclusion applies, that velocity is also some constant. And so I think we should check that out, right? We've written down the velocity, we've written down the position and the velocity, so let's find their magnitudes. So I'm going to go back to where I have position and velocity. I'm going to erase everything else. I'm going to find those magnitudes. And if you're watching the video now, you could go on and pause the video and find those magnitudes on your own. Those magnitudes very well could be for other functions on the variable t. For us, we're supposed to get a constant. All right, so I end up with sine squared 2t plus sine squared 2t, so 2 sine squared 2t plus 2 cosine squared, and I can imagine factoring out the 2. Sine squared plus cosine squared is 1, and so I get root 2. And so on that next board where I had written down that the magnitude of position was always some constant, now I know that's not just some constant, it's the square root of 2. All right, the velocity's magnitude, or speed. 4 cosine squared plus 4 cosine squared, I'll get 8 cosine squareds when I add those together using the distance formula, plus square 2 root 2, and you get 8 sine squared of 2t. And again, factor out the 8, Pythagorean identity, and we get 2 root 2. The speed is 2 times the square root of 2. And so we've verified this conclusion that we know is true and generally true, that when a position vector dot product, its derivative is 0, that function had to be of constant length. This particular example also has a constant speed, and that's not always true. Coming back to this decision, not decision, but this calculation, it tells me that whatever my curve is, it has to lie on a sphere, right? Because the position is of constant length. So whatever my curve is lives on some sphere of radius root 2. Okay, and not just some sphere, but the sphere of radius root 2 whose center is the origin. All right, so number 4 asks me to look at the original R of t and find an antiderivative. And so going back to my original position vector, which was sine of 2t, sine of 2t, root 2 cosine of 2t. I'm writing that down from memory, so I just want to make sure that I didn't make a mistake there. Perfect. And I'm supposed to find an antiderivative for it. All right, you go on and pause the video, find an antiderivative. One way to do it is just to give the antiderivative a name, right? And kind of have it as, if the function was little r, then the antiderivative could be big R, and then just write down some function that has that as an antiderivative. Just differentiating each scalar component. And I would claim this morning that something written down like that is actually an appropriate answer because it just says find an antiderivative. You could also write plus vector c here for that arbitrary constant vector of integration. You could also write a plus c1, plus c2, plus c3 in each part. Since this asks for an antiderivative, this would be an appropriate answer with or without the plus c. Now, in the answers I wrote out and that are posted to Moodle, I chose to answer this question by writing down the indefinite integral of r of t dt. And if I choose to write it down like that, then I am stuck. I have to write the plus c. Because asked to evaluate an indefinite integral, even though I'm the one who chose to write that symbol down, the thing on the other side of the equal sign always has to be the most general antiderivative. And I thought it was important this morning to talk about integration with the vector calculus. But more than anything, I wanted to remind us about these arbitrary constants that for us are now constant vectors, a c1, c2, c3. Okay, so that got us through number 4. Number 5 asks us to write down the arc length parameter s of t from the point where t equals 0. The arc length parameter is a function that takes in t and gives me the arc length from a starting point. And we're told that starting point is when t is equal to 0. I plug in t as my top bound, and then it's the speed of variable tau, the Greek symbol tau, as a dummy variable, right? I can't call this t if I'm using t as the top bound, right? So I replace it with tau. You can actually use any variable you wanted to there. I like using tau. Your author used tau. I've seen books use other notations. Now, we've calculated speed already. We know speed is the constant function, 2 root 2. So this definite integral, pretty easy to evaluate. And there is the arc length parameter, the function s of t. Plug in a t, get out the arc length from that point where t was equal to 0. All right, one of the important calculations we learn in this unit is that if you take ds dt, if you differentiate the arc length parameter, you get back speed. And we can see that here, right? You take the derivative of this, you get 2 root 2. The speed was always 2 root 2. We use this observation a lot moving forward, though. Remembering that ds, right, is the differential of the dependent variable s in the arc length parameter. All right, question number 6. Seems really boring here. Find the length of the curve on the interval 0 to 2 pi. Well, 4 root 2 pi, right? Just plug in 2 pi, 2 times 2 is 4. Beautiful thing. Really easy. Seems almost too boring to be asked. I hope that turns out to be important later on. Otherwise, well, I could have asked you to plug any number in there, I suppose. And then finally, we're asked to describe the curve, r of t. And I want to talk about that, and I want to talk about a way to think about that visually. If you look at the bottom of the PDF, you see a link to GeoGebra. If you're watching this on YouTube, I'll actually put this in the comments. And if you're watching it through Moodle, then it'll be in the Moodle description as well. And so at this point, I guess you could just look in GeoGebra. But let's talk about what we might think about if we didn't have GeoGebra handy. So what I want to think about, that original position vector, everything we know, and different kind of ways to look at the curve in space. And so what I want to do is to look at my parametric equations that are my components in pairs. So I'm going to ignore the z-coordinate for a minute. And what we do when we ignore the z component and just look at the x and y is we're looking at a projection into the xy plane. And so the way to think about that is imagine just looking straight down the z-axis, right? And so you would only observe what's happening in the xy plane. So we don't need to know this. This tells us everything. And the big realization, if I'm just looking in the xy plane, top down on the z-axis, I would get x equals y, right? Because x always equals y. So whatever's going on falls on the line y equals x in the xy plane. Okay. But I also see that y and x are always equal to sine of 2t. The biggest thing sine can ever be is 1. So the furthest away from the origin I can ever be is the point 1, 1. The smallest thing sine can ever be is minus 1. So I get to go all the way down to the point at minus 1, minus 1. And sine takes on every value between minus 1 and 1. So somehow, just looking down the z-axis, it would look like I have a point, if I imagine a point traveling on the curve, going up and down that line segment. All right. So, in the xy plane, I see a line segment. We also know that the magnitude of position is always a constant. So I'm observing something is actually moving on a sphere, but if I look top down on it, I just see a line segment. And this is where, you could pause the video and really think about it, and I think you know what this has to be. Okay, so hopefully you said something out loud to yourself or in your head for what this thing looks like. What I want to do now is look at what this thing looks like in the xz plane. X is sine of 2t. Z is root 2 cosine of 2t. These are actually parametric equations for an ellipse. X squared is sine squared of 2t. Z over root 2 squared is cosine squared of 2t. And so if I look at those two things together, if I imagine adding sine squared to cosine squared, right, I'd get 1. And so, well, sine squared plus cosine squared is equal to 1. So that tells me that x squared plus z squared over 2 is equal to 1. And that's an equation of an ellipse that would live in the xz plane. And I could draw that ellipse. So I have a curve that when I look in the xz plane, so I imagine that I'm looking down the y-axis. And the way I've drawn this, we'd actually be looking down the y-axis like the y-axis was pointing away from us, but we see an ellipse. If I look in the xy plane, like I was looking top down the z-axis, we see a line, and we know our curve itself lives on a sphere of radius root 2 centered at the origin. If I put all of that together, the graph of r of t has to be a circle in space. The line y equals x comes straight out of the first octant towards me, standing here in front of the camera. And so this circle kind of looks like this. Right, from the top down, it looks like a line. If I looked at it on an angle, like I was looking down either the y or the x-axis, I would see an ellipse. Now, just in case my picture wasn't good enough, I actually have drawn the circle we're talking about here. So if I look top down, I see a line. If I look down where the y-axis would be, right, and it's a little hard to see, but I see my circle on an angle and it looks elliptical. All right, and then in space, kind of oriented like this. Okay. Even better than that, the point here is 1, 1. The point here is minus 1, 1, which means that's the square root of 2 in length, and this is the square root of 2 in length, and so this total length is 2 root 2, which is the diameter of that sphere, which means my circle is the biggest circle I can draw on that sphere. It has the same diameter of the sphere, and it goes through the same center point. And I can actually observe that here too, right? I went up root 2 and down root 2 because that's root 2 squared. And so this isn't just any circle, it's what we call a great circle. And I'm not being congratulatory about how I drew it. Now, if you're watching this video and you were in the synchronous class this morning, you now know I made the same stupid joke twice, so I'm sorry about that. A great circle is a circle drawn on a sphere that goes to the center point that has the same diameter. If you're thinking kind of about, maps in the Earth, the equator is a great circle, and so is the prime meridian. And the way this one's drawn reminds me of one of those meridional curves, like a longitude rather than the equator is a latitude line. And so I have a circle that's like the prime meridian. Now, the circle we've graphed has a radius that's equal to the square root of 2. So now, just thinking about the circle and nothing else, I could tell you its circumference is 2 root 2 pi. We evaluated S of 2 pi, the distance traveled between 0, because that was the base point, and 2 pi, and we got 4 root 2 pi. And so this is where we had to go, wait, shouldn't these two things be the same? If I travel the whole way around a circle, isn't that the arc length? So we had to confront this, right? Either we've made a mistake, there's a contradiction, or something else is happening. And of course the answer was something else is happening. By examining the original position vector, we realized that the trigonometric functions in play all have a 2t in there, which means they all have a period of 1 pi. Which means between 0 and pi, we would go once around the circle. Between pi and 2 pi, we go around the circle again. So this arc length, counting the total distance traveled between 0 and 2 pi, is double the circumference. So, no contradiction at hand. All right, that kind of goes through all of those problems. Going to be in touch with the class through email this week more than anything else, so you should get more information. But for now, that's it. There are handwritten solutions to these problems posted to Moodle as well.